Yeah. Also, the link to the feedback form is in the chat, and on that form you'll also find the link for the slides. So as well as the attendance code. So yeah.
All right. So let's get started. So welcome back, everyone. Thank you for coming to the second workshop of Advanced Track. Today we're going to be mainly covering feeding forward and back propagating through a neural network. Okay, so Sudhanshu, Adithya, and I are going to be in charge of teaching Advanced Track this quarter. So if you have any questions, feel free to reach out to us on Discord or come to the office hour. That should be, actually it's 9 p.m. tonight. So yeah, feel free to come by. Okay, so here is our tentative schedule. So today we're going to be we're going to do a review on gradient descent first, and then we're going to be covering, feed forward and back propagation. Okay, so before jumping straight into back prop, so let's do a quick review on gradient descent because it's pretty important to get a good understanding of this before, talk about back propagation. All right, so you all remember what a gradient is, right? So someone want to give me an answer? That'll be pretty nice. Feel free to answer in chat. Okay, yeah, so the gradient of a function is basically a vector that contains all the partial derivatives of the function with respect to each variable. So I think most of you got that, so that's good. So there's this interesting property about the gradient of a function where it always points in the direction of the steepest ascent. So naturally, taking the negative of this vector would point us in the direction of steepest descent, which is super useful when we're trying to minimize our loss function. So our gradient descent algorithm will actually continue until our loss converges to a local minimum. However, there's no guarantee that this particular local minimum that we converge to would be the global minimum for our cost function. Actually, there's another way that the algorithm could terminate, which is when our loss diverges to infinity. But yeah, that's a situation that we want to avoid at all costs. All right, before moving on, let's do a quick exercise on partial derivatives, just to make sure everyone is on the same page. Okay, the poll should be launched. Hopefully you all see the poll. Oh yeah, wait. Oh wait, there are 2 questions. Okay, I guess, yeah, in order to show a second question, I'll have to show the answer for the first one.
We could do the first one and then give it a quick pause and then do the second one. What's that?
Oh. I didn't think
you can press, yeah. Ha, love. Okay, no problems.
Too late.
Well, do it on the second one, guys. No worries.
I don't want to launch the poll twice.
No worries.
Okay, yeah, so the first one is just like I guess an exercise. Just check your answers, make sure you get it. Oh, we got the first one. Oh yeah, so apparently you have to you can pick multiple answers for this question, so keep that in mind. I think some of you only picked one answer. Okay, I'm gonna give it, I guess, another 10 seconds. All right. So I think most of you got the right answer, so that's good. All right, so let's move on. Okay, so in order for our gradient descent algorithm to function properly, we have to find the right value for this value called the learning rate. So the learning rate is the step size of our gradient descent algorithm, and so it basically determines by how much we adjust our weights with respect to the loss gradient. So mathematically, the learning rate is represented by the alpha in the expression at the top. So the reason why picking an optimal learning rate is so important is because if we pick a learning rate that's too small, our loss function will take forever to converge. If we pick a learning rate that's too big, then our loss might overshoot the minimum and even diverge to infinity, which we talked about earlier. So traditionally, we just set the default for the learning rate to 0.1, something small like 0.1 or 0.01. But there has to be a smarter way, or there are smarter ways to do this. So this is where optimizers like Atom, Momentum, and RMS Prop comes in. So what these optimizers are, there is just basically variants of the gradient descent algorithm that changes the learning rate during training in a very smart way that basically help overcome these problems. So if you want more details on how these optimizers work, feel free to attend our Advanced plus track, where we'll be going into those in detail. So I guess for those of you who just want to play around with different learning rates, feel free to check out the simulation developed by ACM Hack. But we're not going to go into it this workshop because we have a lot of content to cover. Okay, so any questions regarding to learning rate and gradient descent? Okay, the chat does not have any questions. Okay, I'm going to hand it over to Adithya in that case, who's going to talk about neural networks.
Okay, cool stuff. Let me just share. All right, I hope everyone can see the slides. We're going to get started with neural networks. So yeah. So what are neural networks? So very basically, this is kind of what a really basic structure of neural networks are. So you have a few layers here. You have the input layer, two hidden layers in this example, and an output layer. So we're going to start off by defining a few terms. So this right here, this node, it's called neuron, which makes sense. It's a neural network, a network of neurons. And within these neurons, you have some value between 0 and 1. And that value is known as the activation of the neuron. All right. And that is essentially the input layer. The input layer consists of all the inputs that we provide into our neural network. It's the layer that we interact with in a sense to provide our neural network with essentially the training or the testing data. After that comes the hidden layers. The hidden layers are, as they're called, hidden, and they're known as hidden because we don't interact with them directly. They're hidden to us. We don't know what's going on there. And usually in this example, it's 2 layers, but in reality, they could be many. More than just 2 on most occasions. And finally, we have the output layer. In this case, we only have 1 neuron as the output layer, which means that the output of this neural network is simply some value between 0 and 1, which is essentially predicting true or false, yes or no, binary classification. But in most cases, you can have multiple neurons in your output layer. And obviously, if that was the case, then you need to have connections from each of the previous neurons in the previous network to previous neurons in the previous layer to be connected to each of those neurons in the output layer. All right, quick question. Let's see. How many layers does a neural network have to be considered a deep neural network? Let's see. I don't know actually. Do you guys want to? Do you know? One of you guys can like pick up on that?
Yeah, I'm not sure either. It's I'm pretty sure there's a lot of debate on what that is, but I guess anything more than a couple is pretty deep because it's already pretty computationally expensive.
Mm-hmm. Yeah. So I hope that answers your question. Yeah. Let's for now we'll just stick to the basics as we kind of try to understand how neural networks work and what their structure are. So yeah. Let's zoom in on a single neuron. So obviously these are known as artificial neurons, and this is essentially their basic structure. You have, as you said before, some activation Y in the neuron, and then we have a whole bunch of activations for the neurons from the previous layer. And each of these neurons is connected to this output neuron with activation Y. And each of these connections is essentially a weight. So this is reminiscent of logistic regression. A single neuron in a neural network is similar to how we do our calculations for logistic regression. We have a bunch of weights. We have a bunch of input values, x0 to xn, and the way we calculate the activation Y is by just taking the weighted sum of all the inputs, adding on some bias B, and applying the sigmoid function to it. And the sigmoid function obviously helps us to squeeze the activation of the neuron to a value between 0 and 1. So yeah, that's really quickly how a basic neural network looks like and how a single artificial neuron looks like. So are there any questions before we begin to move forward? All right, cool. So let's take a look at the activation function. So for this workshop, we're going to be using the sigmoid activation function, but there are a lot, and in reality, we don't use sigmoid as often nowadays. One example of an activation function that is used is ReLU, which is essentially taking the maximum of either 0 or your input value x. So that means the graph essentially looks like this. And once you reach the origin, it shoots up like that. But yeah, that's just another quick example of another activation function that is used. But for right now, we will use sigmoid. And the sigmoid function should be fairly familiar to everyone here, because we've used it a fair amount in beginner track. So yeah. So quick recap. Logistic regression, very similar to having just a single neuron with a whole bunch of neurons connected to that output neuron. And then with a neural network, that's when things begin to get a little bit more complicated, where you have multiple neurons in every layer. And we have weights connecting every neuron in the previous layer to a neuron in the next layer. So yeah, are there any questions? Feel free to put them in chat or unmute. All right. Cool. So I guess one thing we could cover real quick is our biases. Why do we need biases? So before I go into that, there's a really great video by 3Blue1 Brown, a very cool YouTuber. Check out his videos actually about neural networks. They're pretty good, pretty informative. But yeah, why do we need biases? So at certain point in time, we want our neuron to be quote unquote activated, essentially having a value close to 1 when under certain circumstances. Let's say before we apply the sigmoid function, we get the output of a neuron to be some value like 0.1 or 1, or it's essentially a small positive integer. When you apply the sigmoid function to that gives you an activation close to 0. Close to 0.5, which you wouldn't necessarily call quote unquote activated. You usually would call a neuron to be activated when it's closer to 1. So we have biases so that we can kind of nudge our neuron's value to be closer to 1, essentially, to make it activated. So yeah. But yeah, again, check out this video. It's really quite useful when it comes to explaining why biases are useful. All right, let's move on. So how does the flow for a neural network work? So first we have to define our architecture, and there are a lot of different architectures out there. We have CNNs, RNNs, and we will be getting into CNN and RNNs later in the quarter. But right now we're just dealing with a simple neural network, and I think that's a good starting point. And then we need to determine our a few initial values, just like number of inputs, or the number of hidden layers we have, and the number of outputs we want. And in fact, this value, the hidden layers, determining the hidden layers, that's known as a hyperparameter, because it is something that we as the designers of a neural network need to come up with before any sort of training happens. So weights and biases, these are not hyperparameters because they are determined through the result of training. Hidden layers, the number of hidden layers we want to use in our neural network, that is hyperparameter because we decide on how many we want for the number of hidden layers. but we will be going more into hyperparameters later in this workshop. And then we initialize our weights and biases. They are initially randomized. So our neural network performs terribly off the bat. But that's where the training part of the neural network comes in. So after that, after initializing weights and biases, we feed forward through our network, which essentially means calculating the activations for all the neurons in the network. And then we backpropagate. And the backpropagating allows us to compute a cost function, which gives an idea of how bad or good our neural network is doing. And then using the gradient that we get from backpropagation, we update our weights and biases. And we keep doing this until our neural network performs the way we want it to, or at least to the standard that we want. But we will be getting more into backpropagation once again later in this workshop. So, all right, let's take a look at notation, because notation is when things get a little bit wonky. So, the way we represent weights is like this. W subscript JK and superscript L. A little weird, but that's how it is. And so essentially the L refers to the layer that the weight is essentially connecting to. And you have K, K is the neuron from the previous layer, and J is the neuron from the L layer. So a very simple way to look at it is using this example. So right here we have subscripts 2 and 4. So this 2 right here refers to the second layer, a second neuron in layer L, and here L refers to 3. And the 4 in the subscript refers to the 4th neuron in the L-1 layer. And since we know our L in this case is 3, and the L-1 layer is layer 2. Another quick example is, let's say, weight with layer 2 and subscripts 3 and 2. So essentially that means this 2 refers to layer 2. This 3 refers to the third layer, third neuron in layer 2. And this 2 refers to the second neuron in the L-1 layer, which is layer 1. Yeah, are there any questions regarding this? All right, cool. Yeah, so whenever you see some weight represented with these subscripts and superscript, this is how you kind of figure out what neurons this weight is essentially connecting and referring to. So in this case, it's this neuron right here. Here's your question. So the arrow points forward, but we try to go back. Yeah. So right now we're in the phase of feeding forward. And feeding forward obviously means pushing through from the input layer to the output layer, and that's why you have these arrows pointing forward. But when it comes to backpropagation, that's when we begin going backwards through the network. We'll be getting into backpropagation again, as I said, later in this workshop. But the arrows essentially are there to get us, give us a better understanding of how the neural network structures are designed, where each neuron in the previous layer is connected to every single neuron in the next layer and every layer after that. So yeah. Cool. So those were weights. The notation for weights is by far the weirder thing. But the notation for activations and biases are pretty simple. So having, let's say, this function, this example, a subscript 1 superscript 3 obviously refers to the layer we're on, the layer that the neuron is on, and 1 just refers to which neuron in that layer, in this case, the first neuron. So you can read this activation as the activation of the first neuron in the third layer. Similarly for biases, in this example, same thing as the activation. This is the bias of the neuron in the second layer, the bias of the neuron, the third neuron in the second layer, essentially. So yeah, not as complicated as the weights. All right, so this is when things get a little bit more wonkier, I would say. So so now we're going to look at how we calculate activations for some neuron J in layer L, in a very general term. I think the best way to kind of demonstrate this is just by drawing things out and giving you guys an understanding of how that works. So, so here we are. All right, so this is essentially the equation you use to calculate the activation of a particular neuron. So let's say we have two layers. We'll take layer 5 and layer 6 of some neural network. And in layer 6, we have some neuron with activation A, J, and 6. So we read this as the activation of the jth neuron in layer 6. And obviously with the activation, this particular neuron has some bias, again, that we indicate like that. And let's say in layer 5, we have 4 neurons. And each of these neurons are connected to this jth neuron in layer 6. So this would mean the first neuron in layer 5 has activation A sub 1 superscript 5, A2 5, A3 5, and A4 5. And if that's the case, then these weights will be essentially, as I said, the first subscript refers to the neuron that the weight is pointing towards. So that's going to be obviously in this case the jth neuron, and the second subscript is the neuron from which the weight is emerging from, and that is obviously in this case the first neuron. So and the superscript is the current layer that we're referencing, which in this case is layer 6. So yeah, so the first weight is W sub J1 superscript 6. Then we have sub J2 superscript 6, J3 6, J4 6. So I hope this is kind of giving you a better understanding of how this is looking. So we have some activation the jth neuron in layer 6. And this is going to be equal to this weighted sum. So WJ1 6 into A15 plus VJ2 6 A25 plus dot 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 plus BJ6. And obviously we need to apply the sigmoid function here. And that is essentially what this summation is, what this summation here that we defined earlier is representing. So we are looping through K here, K being the number of neurons in layer 5. And we are essentially looping through every single weight and its corresponding activation in layer 5 and just summing them up, slapping on the bias at the end, and then applying the sigmoid function to it. So yeah. Are there any questions before we move on? All right, let's keep moving. Yeah, so this is another diagram we can look at, obviously, to kind of figure out how all these calculations are happening. So in this case, we have this summation connecting all the weights to the first neuron in layer L, and looping through all the K layers in layer L minus 1. And here K is equal to 3 for these 3 neurons. So we loop through obviously all K neurons in layer L minus 1. And we multiply that with all the activations from the previous layer. Once again, we're looping through K, and we slap on the bias at the end, and then applying the sigmoid function gives us the activation for the first neuron in the second layer. So yeah. So obviously that's a lot of writing, and we don't want to write too much. And that's why we have matrices. Matrices help us condense things down. So they're essentially less chaotic. So once again, we can look at an example. So we have so a good way to think about this is we have some vector here, and the activation is going to be a vector. It's going to be a column vector consisting of all the activations in layer L minus 1. Similarly, this vector here represents all the activations of the neurons in layer L. So we can write that real quick as A1 L minus 1, A2 L minus 1, and so on all the way to the end. And right here, AL 1, AL2, and so on. The weights though, this is in fact a matrix. So the way we can think of it is as so. And the way the matrix is designed for the weight matrix is the first row consists of weights W11, W12, all the way to W1J. And here we have W21, W22, all the way. And as we get to the end, we have WKJ. So essentially what's happening here is all the, every single row in the weight matrix corresponds to the weights connected from the first neuron in layer L. So all of these weights are essentially in this first row right here, for any single row. These consist of all the weights connecting to the neuron in the next layer, which is going to be the first neuron. In the first example, the second neuron, the next example, and so on. Yeah. So as you can see, because the order we choose a subscripts in, all these weights are just really nicely arranged, including the subscripts. Yeah, so we're going to get to the biases. The biases are not a matrix. They're a vector as well. VLJ, not J, sorry, VL1, VL2, all the way to BLJ. Again, just to make this a bit more clear, we go all the way here until A of L minus 1K. And obviously this is K and this is J. How do you calculate the biases? The biases are initialized randomly, and once we backpropagate through the neural network, we learn how to set those biases so that they give us a better output for all our training data. So we'll be getting towards how do we calculate biases through backpropagation later in the workshop. So yeah, we have in this vector right here, K elements, in this vector J elements, and every single row in the weight matrix corresponds to the, so essentially the ith row in the weight matrix includes all the weights connected to the ith neuron in layer L. And every column, let's look at the first column in the weight matrix. This first column represents all the weights from the first neuron in layer L minus 1. So so yeah, it's a little weird to like wrap your head around because with neural networks with more, like a lot of neurons in every single layer, and having weights connecting every single neuron in one layer to every single neuron in another layer, there's a lot going on. And as you keep looking at neural networks and kind of understanding how this notation works, eventually things will get clearer. So so start small, have like smaller neural networks and expand from there. So yeah, we can move on. So yeah, this is the essentially the compact way of using matrix notation to represent or to calculate activations in a neural network. So yeah, this Z refers to just a weighted input. It's the weighted input vector containing all the weighted inputs. And once we apply the sigmoid function to it, that's when we call it the activation of that particular neuron. So yeah, all right. And once again, this is another way of looking at how each of the layers translate to the vectors. So here we have obviously the activations from the first layer. Right here, after we do our initial calculation to get the weighted inputs with the bias, that is the quote unquote z value, which is just the weighted input vectors. And once we apply the sigmoid function, that's when it becomes the activations of all the neurons in the second layer. Perfect. And yeah, looking at this will give you a better understanding of how why these matrices or the use of these matrices and vectors gives us the activation of each neuron. So how many neurons are in layer L? Simple enough. We just need to look at the vector with the weighted input values from layer L, and as you can see, there's only 3. So there are 3 neurons in layer L. And how many neurons are in layer L minus 1? Also pretty simple. Look at all the look at the number of activations in the vector with the vector of the L minus 1 neurons, in this case 5. So we have 5 neurons in layer L minus 1. So yeah. Cool. Yeah. So yeah, as Jenson said, A is the output of the previous layer, specifically A with subscript L minus 1. L minus 1 refers to the previous layer. And as you can see, we have an L here. That L corresponds to the current layer that we're on. Yeah, cool. So, and with all that notation in mind, we can now understand how feeding forward works, because we now have a way to calculate all the activations of all the neurons in our neural network. We just have to keep doing that for every single layer, all the way from layer 1 all to layer L, capital L, which refers to the output layer. And this gives us, at least initially in our first run through of the neural network, a really bad neural network. And that's the point of feeding forward. Feeding forward helps us understand if the neural network is doing what we want to, essentially. And after we feed forward, that's when we begin to backpropagate to figure out how we can change our weights and biases, tweak them in order to make our outputs more fine-tuned to what we expect them to be based on the input. Okay, so we have a quick question. I will stop sharing. Before we do that, are there any questions that we have? I'll give it a few minutes if anyone wants to think of any. Is feeding forward basically what we were doing in beginner track? Let's see. Yes, I mean, you're technically doing both. You're feeding forward to get your output value, values. And then you're also applying gradient descent in order to figure out how we can change our weights and inputs. So we're in beginner track, especially with a logistic regression, we, as we said, like at the start, logistic regression is essentially a single neuron. So is a single neuron a neural network? Maybe. But right now what we're doing is we're putting all these together. We're putting all these together to create a much more complicated neural network that that again, and that's when things like feeding forward and backpropagation makes more sense in this context. So yeah, I hope that answers your question. Cool. Yeah, so we have a quick poll. I don't think we have an actual poll for this, but I think people can just go ahead and put their answers in chat.
We do have an actual poll for this, actually.
Oh, we do? Oh,
yes.
Perfect. I did not know that.
Let me launch that real quick for you. Slide 23. Okay.
Oh, great. Perfect. Okay, we'll give it another 10 more seconds. Alrighty. So most of y'all, the majority got it right. So these questions are kind of low key, meant to trick y'all. So the third one is the right one, and it seems like a lot of people chose the fourth one, which is understandable. There's only a small difference between both of these, but it's important to keep in mind that we are always going to be looping through all the neurons in layer L-1. So in the fourth example, we were looping through J, which means we're looping through all the neurons in layer L. That's not the case. In reality, we're looping through all the neurons in layer L-1, which refers to subscript K. So if anyone has any questions regarding this this poll, let me know now. We can take a look at it. All right. Sounds good. In that case, I will hand it off to Sudhanshu, who will take over backpropagation.
Okay, awesome. So what we've just learned is how to send our inputs through the neural network and get these activations and compute some cost. Now, our objective is to learn some parameters, the weights and biases that some of you were mentioning in the chat. So that's what backpropagation allows us to do. Now, fair warning, there's going to be a good amount of math, linear algebra, and calculus coming up. But kind of the analogy to keep in mind through all of this is that backpropagation is chain rule. Like, it's not like the chain rule, it is chain rule wrapped up in a slightly fancy wrapper. So keep that analogy in your head, and this should make it a lot more smooth. And throughout these slides, we're going to be using the notation in Michael Nielsen's book, Neural Networks and Deep Learning. It's a great book, by the way, for those of you who haven't checked it out. And the second thing, we're going to show a lot of seemingly magic formulas. We're going to just plop an equation on the screen and be like, this is what it is. And the reason we can't do all these proofs is obviously we're short on time, but we have a link over here where one of our officers, Payman, actually worked out the proofs for all of these formulae, and you can check that out here as well. So let's get started. Well, what is backward propagation? So I'm going to be calling backpropagation backprop for short. It's what everyone calls it. And formally, it's the backward propagation of errors. Now, so far we've been kind of, loose about error and cost. We say error, cost, loss, etc., etc. We're going to be a little more precise from now on. We're going to call cost that final output that we see, that mean square error kind of term. So this quadratic cost. And we're going to define error on the next slide. Now, what we're going to do is, our final objective is to take the partial derivative of C with respect to each weight and each bias. So we could have like 100 million weights and biases, which is not even unreasonable. And we need to find the derivative with respect to each and every single one of them. Now, that's not an easy task, but the smart people who did all the math of this figured out that through backpropagation, you can do this all in one fell swoop. So you can calculate all these gradients all at once. So these are the quantities that we want to find: del C with respect to del W, del C with respect to del B. Okay, so now let's define what the error is. So the error, we define it to be the partial derivative of the cost with respect to the weighted input vector Z of the jth neuron of the Lth layer. So let's break that up once more. The partial derivative of the cost with respect to Z, where Z is that weighted input vector Wx plus B or whatever. And we take that to the jth neuron at the Lth layer. And the notation we use for that is del J L. So it's similar to what we've seen before. And so intuitively speaking, it's kind of saying how much does the cost depend on that one particular neuron. Seems pretty intuitive. And we'll note here that we define the error in terms of Z instead of A. And the reason the author has chosen to do that is for algebraic convenience. We'll see how it all ties in later on. Now, we should also note that this error isn't the final step. Like, this isn't the gradient that we're looking for, but it's an intermediate step that's going to help us get to that partial derivative. And of course, it does help because the partial derivative does in fact depend on what the weighted input has to be. Okay, so real quick, does anyone have any questions on the last couple of slides? We're going to be taking this pretty slow because I want to make sure it really sinks in. Okay, there we go. So this is basically showing the importance of each neuron to the overall cost. Yes, exactly. So we'll be a little more precise. It shows the importance of the weighted input to a particular neuron to the overall cost. So yeah, it will contribute to how important each neuron is. Okay, any other questions? Also, if the term seems a bit mysterious, don't worry. It's defined this way for algebraic convenience. Are there other factors that contribute to the neuron's importance? Yes, absolutely. And this is, like I said, only one part of the equation. And we're going to add in some other parts to get the total picture of what the gradient should be. Okay, let's move forward. So now we're going to define something called the Hadamard product. Now, this is going to be like, trust me, it's going to be really, really simple. The Hadamard product is essentially the dot product without the addition. So it's an element-wise product. We have a vector, 1, 2, another vector, 3, 4, and the Hadamard product between these two vectors is simply the element-wise product. So we take the first element, multiply the first element, second element, the second element. It is the way you wish matrix multiplication was, but it really isn't, right? So it's literally element-wise multiplication, and it's really nice, really simple. Okay, so the first step in backpropagation is to calculate the error, that quantity you defined earlier, the error for the final layer, the output layer. And the way we do that is using this formula. And like I said, the formula is a bit magical, but the proof is in that link we have. So the error for the jth neuron of the last layer, so the last layer is this capital L, that error is defined to be the partial derivative of the cost with respect to the activation times sigma prime evaluated on the weighted input. So sigma prime is the derivative of whatever activation function you've chosen. So it could be tan H, relu, sigmoid, whatever. And that's an easy derivative to take. We can do that in high school calculus class. So of course, we don't like sub indices. It's a pain. So instead, in nice simple vector form, using that Hadamard product, we define it like this. So it's simply the gradient with respect to A of the cost corresponding to this term right here, Hadamard product with this derivative of the activation function evaluated on Z. So this gradient of C with respect to A is also a vector where each element is a vector of J elements where each element is this term right here. And I promise on the next slide, we're going to have some matrices completely fleshed out where this looks a lot more clear. But for now, this is what it looks like as a formula. And now you can ask, well, this function is really easy to compute. We have the Z, we have a nice analytic formula for the sigma. The way we calculate this term, or the same thing, this term, is simply by taking the derivative of that cost function. So way earlier, we defined the mean squared error cost function. The derivative of that ends up being this formula here. Again, a little bit hand-wavy how this came about, but this is what the formula ends up being. And in fact, if you all have done linear regression before, this formula is exactly the same as it was back then, because the cost function hasn't changed. This quadratic cost function is the mean squared error, and the derivative of that is exactly the same. Okay, so let me do this slide here. So in vector notation, much nicer, we have this long vector corresponding to the partial derivative of the cost with respect to each of the activations. So this gradient vector right here, Hadamard product with the sigmoid, the derivative of the sigmoid evaluated on the weighted input. So we have this vector, Hadamard product with this vector, which gives us another vector. Okay, let me pause here. I know we did a pretty big concept, so does anyone have any questions? Yes, exactly. So let's be a little more precise again. This gives us the overall error for the final layer. So we're going to be defining it for a general layer in the next slide, but for the very final layer, the capital L layer, this gives us the overall layer. Okay. Yes, absolutely. So the reason it's called backpropagation is because we do the output layer first, and then we work our way inwards. So yeah, so this is done first, L minus 1, L minus 2, and we go backwards. Does that make sense? Okay, awesome. Any other questions? Okay. So now, like Jacob mentioned in the chat, now we need to calculate the errors for the other layers. So we have our output layer, it's ready, good to go. We want to use that value, that all that hard work we put in, use that value to calculate the error of the other layers. So now you just start thinking a little bit of chain rule. Think about it, the outermost function somehow contributes to the inner function, to the inner function, to the inner function. So the chain rule analogy should start coming through now. So the vector form, I'm going to jump straight into the vector form, is this formula right here. Again, disclaimer, it's the proof of this formula is in the notes. I definitely recommend checking that out. So, but to walk through this formula, right, the error for an arbitrary layer L is defined to be the, so what we do is we take the error of the L+1 layer, this is the error that's ahead of it. We multiply that by a weight matrix of that L+1 layer. We take that entire quantity, Hadamard product, with the derivative of the activation function evaluated at the weighted input of the current layer. So obviously when I say it, it sounds long, but it's literally this one line of code or one line of this one line equation. So the takeaway, the formulas are obviously irrelevant, but the takeaway is that we use the error of the next layer to calculate the error of the current layer. And that's what's important. So if you want to calculate this, we better have this already. So that means we need to go backwards. We need to calculate this first and then go on to this layer. Right. So visualized, not being scared by all this LaTeX, what's happening is that we have this gigantic matrix here, which corresponds to W. Then we have a vector, which corresponds to the error of the L+1 layer. So we take this entire quantity, perform a good old matrix vector multiplication, take a Hadamard product with this quantity right here. So this is what the formula is, and very simply, it gives you that error for the arbitrary Lth layer that you've chosen. Okay. Are there any questions about how we calculate this error? Okay, so we have a question. Why does the error depend on the layer after itself? That's a good question. So let's think about it this way. After we've done all the feed forward, we've taken our inputs, passed it through all these matrices, all these activations, done all this work, and we get this cost in the end. Let's say we're classifying cats and dogs, and we predict a cat is a dog or something like that. We get this final cost. Now this cost is only visible to that very final layer, that last layer of the network. But the output actually depends on the entire neural network, all the previous weights and biases. So what we need to do is we want to take that cost, take it to the previous layer, see how much the previous layer contributed to that cost, take it to the previous layer, and see how much it contributed to the cost. So like the chain rule does, it takes back the error from that final output all the way up to that first input. Does that help? Okay, cool. Any other questions? Okay, awesome. What is the T on the weight matrix again? So the T is simply transpose. The weight matrix, we take the transpose of the weight matrix instead of just the regular weight matrix. Cool. Any other questions? This all requires the learner to be supervised, right? Yes, absolutely. So this is the supervised learning model, because when we did our forward propagation, we calculated our predictions and we compared it against the ground values, the true values. Once we did that, we got some cost, which is what we're backpropagating and doing all this extra work for. So yeah, so the cost depends on some supervised learning model. Awesome. Okay, let's go on to the next slide. So now we have our beautiful error vector, and we want to use that to calculate the partial derivatives of the weights and biases, because that is our final objective. Because if you remember from back in, when we were in kindergarten and we did linear regression and gradient descent, we needed the partial derivatives. So we have one step towards that, and now we want to calculate that final value. And it turns out it's super, super simple. In the case of the biases, the partial derivative happens to be this vector itself, which is really, really convenient. I mean, that's fantastic. We can go home. And the partial derivative of the weights we add this little extra term, not quite as beautiful as this, but still pretty nice. So we calculate this common term for each of these, and we simply multiply with this activation. So to quickly recap the notation, we have this final cost, we have a weight of the Lth layer, the Jth neuron of the Lth layer, connected to the Kth neuron of the L-1th layer. And the formula is simply this value right here. We take the activation of the previous layer, multiplied with the error of the current layer. Okay. And to nicely summarize the equations we just learned, we have the error for the last layer, the error for an arbitrary layer, the partial derivative of the biases, and the partial derivative of the weights. So that's the entirety of backpropagation right there. And yeah, so does anyone have any questions about that? So we have a question. We're going to be running these partials and adjusting every layer at once. So yes. Okay, I'm going to say, okay, I'm not sure I fully understand your question, but what I'm going to say is once we get the cost, we're going to take one swoop through the entire network and calculate all the partials for all of our layers. Once we have that, we have all these partials, we simply update all the weights of our network. Does that help? Okay, perfect, great. Any other questions? How many times do you usually do this process? Okay, so that's a good question. And the answer, unfortunately, is that it depends. So the number of iterations of gradient descent is unfortunately going to be a hyperparameter. So you're going to have to play with it, increase it, decrease it, lots of stuff. So unfortunately, it's very experimental. The way you kind of figure out that it's working is by observing that cost. If it's going down and it's not going down any further, you're pretty much done. Cool. Yeah, absolutely, you're welcome. Any other questions? Okay, let us move forward. Okay. So now we have all the ingredients, right? We have our partial derivatives of the weights and biases. So now we're gonna, take a step back and perform our good old-fashioned gradient descent. So stuff we're all, experts at this point. But let's add a little bit of a twist to it. So we all know how to perform gradient descent. Take the old weight, subtract a partial derivative, multiplied with some learning rate. But the issue with that is that it's very, very, very slow. So a technique we're going to use is what we call mini batch gradient descent. And in the next few slides, Jenson's going to really flesh this out. But to quickly show you what the formulas look like to kind of wrap up our discussion of neural networks really nicely, what we essentially do is, well, the same thing we were doing all this while, except with this little extra thing over here. So we take our old weight and we subtract some learning rate eta, and this is our partial derivative term. So let me take a quick backtrack here. The partial derivative looks like this. It's del L sub j. What we're doing is simply taking del L sub j for each and every data point x. When we do that, we sum it all up and we get a vector. Once we get the vector, we multiply it by a learning rate. Once we get that, we subtract it from the old bias. Similarly, for the W's, this entire scary term is simply the partial derivative. So this expression spits out some vector, which is the partial derivative, which is what we spent the last 20 minutes trying to figure out. This is what that term computes. And we simply update it like we would normal gradient descent. So eta, this n symbol, is the learning rate. M is the mini batch size, which again, we're going to be discussing in the next few slides. and X refers to all the samples. So all the training samples that we have, we iterate over all of them and sum them all up. Okay, any questions at this point about gradient descent or anything else? Okay, I think we're good. Let's do a quick poll to kind of make sure we're all comfortable with what we just covered. So let me launch this poll. Give me a second. Great. So, oh no, yeah. I apologize. Give me 1 second. So you should see the question on the screen right now. It's simply figure out what all these values mean, because we've covered a lot of notation, a lot of symbols in this workshop. I want to make sure everyone is really comfortable with what we've done. And definitely take a second to look at all the options. Some of them are meant to be a little misleading. So okay, about halfway there. A few more people. I'm going to give it like 10 more seconds. Okay, we can call it here. Let me share the results with y'all. So yeah, so absolutely. So number 2 is correct. So let me actually see, what are the other results saying? So you have a couple of people who said number 1, and I guess the partial derivative here is a little confusing, and that's fair, right? That was the trick in this question, after all. But I hope it's clear that this notation that we spent the last half an hour defining is in fact the error, and that's how we define it here. Some other person might have chosen a different notation. Michael Nielsen chose this, so that's what we're sticking with over here. And of course, Z is the weighted input, which is WX plus B, and A is the activation. I remember it because I'm really creative. A is activation, right? So it's a very powerful mnemonic to remember. Awesome. So I think we're good. Does anyone have any last minute questions about the poll? Otherwise, I'll hand it over to Jenson. Okay, go for it, Jenson.
All right, can you guys see my screen?
Yep.
All right. Okay, so the motivation behind using a mini batch gradient descent is when we're working with really large data sets, the regular gradient descent algorithm can be kind of slow because considering it has to go through an entire data set, taking the average of the gradients for each sample before making an update to the weights. So compare that to mini batch gradient descents where we only have to go through it only has to go through a subset of the data set before making an update. So this actually like speeds up the learning process significantly when we're working with large data sets. So another motivation behind mini batch gradient descent is mini batch gradient descent was known as a stochastic algorithm. So for those of you who are not familiar with the term, a stochastic algorithm has some degree of randomness to it that causes its output to be non-deterministic. So in the context of training neural networks, so every time you run mini batch gradient descent, you're going to end up with a neural network that's slightly different because essentially what we're doing is we're updating our weights in a slightly different way depending on how we partition our data sets into mini batches. Okay, so let's actually walk through a concrete example. So let's say our starting point is somewhere around where the red ball is on this graph that represents our cost function. So if we're doing regular gradient descent, we're going to end up at the local minimum to the left like 100% of the time. So what that means is we're gonna miss the global minimum to the right. Okay, never mind. I thought that was the question. Okay, I got distracted. Okay, but so if we're doing mini batch gradient descent, then sometimes we might actually end up at the global minimum to the right because we're taking the gradients with respect to only a subset of our data set. So that actually might cause our loss to move to the right, even though that actually increases the overall cost of, the overall cost for our network. So so basically doing so might actually allow us to find other minimums that are lower than the minimum that we'll usually end up in. So that's a good thing. All right, any questions regarding to the motivation behind mini batch gradient descent? Okay, good. Okay, so so someone actually asked about hyperparameters like last workshop. So let's actually talk about hyperparameters for a second. So to perform mini batch gradient descent, we'll need to choose certain hyperparameters. So the reason why picking the right values for hyperparameters is so important is because hyperparameters control the entire training process of our network. So usually hyperparameters are not tuned by the training algorithm itself. Instead, they're provided by the users. So in this sense, weights and biases are not hyperparameters, they're just regular parameters. So the learning rate of our gradient descent algorithm is an example of hyperparameter because that's the step size of our network. Is that a question? Oh, wait. Okay, I misclicked. Question, the mini batch is just a smaller set of data that we run on. Yes. So basically what happens in mini batch gradient descent is we partition our entire data set into mini batches of size M. And then we basically just run like, we run like a mini batch into our network, and then we update our weights once for every mini batch. So after we run like all the mini batches, then we've effectively like seen the entire data set once, and that's considered to be one epoch. Okay, here's the second part to the question. Where does the local / global min on the previous graph come into play? Okay, that's a good question. Wait, hold on. Okay, so this graph represents our cost function. So usually a cost function has multiple like local minimums and a global minimum. So what we actually want is for our model to converge to the global minimum, because that means our model is having the best performance that it possibly can. But depending on like different starting point, we might end up in like some local minimum, which will lead to suboptimal performance. So what a stochastic algorithm does is there's a degree of randomness to it. So it might discover other global like minimums that are lower than the one we normally would end up in. And so once we discover a minimum that is better than the current one, then we'll basically save the set of weights, or the final weights. And so that's one advantage that a stochastic algorithm like mini batch gradient descent has, because it's basically a more efficient way to find the global minimum, which will lead to the best performance for our network. Okay, so yeah, the mini batch size is another example of hyperparameter. Okay, there's another question. So do mini batches build on each other, or are they run independently? Okay, so I guess, okay, let me try to understand this question properly.
Sorry.
Are they run independently?
Basically, I was kind of just wondering, like with the mini batches, is there, when you run a mini batch, does the information from the last batch come into play with the new one? Or is it just like running each one over and over and seeing where you find the best global minimum for it?
Okay, so for each mini batch that you run, you'll effectively make an update to your weight. So I believe that is discussed earlier. Okay, yeah, so yeah, every time you run like a batch, you'll make an update to your weight. So so this is like an approximation to the actual gradient, but it's not perfect because we're only using a subset. But yeah, I guess like each batch is independent of the other, except for the weights because they obviously carry over. That what you
Okay.
mean.
Yeah, that cleared things up.
Okay. All right, so another example for hyperparameters is the number of layers in the network. So this is actually slightly different from the previous two examples because learning rate and mini batch sizes are hyperparameter for the training algorithm, so the gradient descent algorithm. But the number of hidden layers in the network is the hyperparameter of our model. So they're tuned in the same manner, but yeah, they're slightly different. Okay, so one pretty common question at this point is how does changing the batch size actually influence the performance of our model? So the general trade-off at a very high level is smaller batch sizes will make the model learn faster, but they're also more volatile. So if you look at let me clarify this. So the y-axis here is the accuracy, not the error. So like a higher accuracy means our model is performing better. So for a batch size of 4, you can see the accuracy spikes up to 0.8 like almost immediately, but then like there are these like jumps, like it's really like volatile because they go up and down depending on the batch size. But if you look at the graph or the batch size of 256, you can tell it learns a lot more slowly, but it's also more smooth. So yeah, that's the trade-off between having different batch sizes. Okay, I guess, okay, the question in the chat is answered. Okay, yeah. Okay, so far we've been discussing neural network in the pretty abstract sense. So let's actually go through a concrete example, and that is the MNIST dataset of handwritten digits. So a single input and output pairing in this dataset would be, okay, so input would be a single 28 by 28 array of pixels that represents a handwritten digit, and the Y value, which is the label, would be an integer that denotes what the handwritten digit actually is. So note that this data set is all in grayscale. So yeah, so there's no like different colored channels that we have to deal with. So that's always good. Okay, so let's talk about the structure of this data set. So the MNIST data set contains 70,000 input and output pairs. So the first 60,000 pairings is considered to be the training set, and the last 10,000 pairing is our testing set. However, in practice, like we usually would shuffle the entire data set before making the split, just to make sure like there's no potential bias that we're introducing to our data set. Okay, so why do we actually need a test set? So in our MNIST dataset example, we could have used all 70,000 dataset to train our network, but instead we're reserving 10,000 datasets a test set to evaluate our network on. Okay, so the goal of training a neural network is not to memorize our data, which is what overfitting is. So instead, we want a model that is able to generalize to real world data that hasn't been seen before. So as you can see from this graph, like a general trend during training is the test error and the training error usually like decrease, both decrease at first, and then there's usually after like a certain point, like test error would actually start increasing, and the test error and the training error would basically diverge from each other, and that's a telltale sign that our model has started to overfit. So what that means is it's basically memorizing patterns in our training data set that would actually like lower its ability to generalize to data that hasn't seen before, which is represented by the test data set in this case. Oh wait, actually I was gonna, okay, so the most easy way to combat overfitting is just stopping before the training error and the test error diverge. And this is called early stopping. So if you stop at this point, then you can see the test error is the lowest. So that means our model is having like the best performance when it comes to generalizing to real world data that hasn't been seen before. Okay, I'm gonna pause for a second for questions. Try to open chat. Okay, it looks like we don't have any questions in chat. Okay, yeah, I guess I'll just carry on. Okay, so let's talk about the difference between a validation set versus a test set. So like I get like the validation set and test set is kind of confusing because of the terminology. So what a validation set really is sometimes a portion of the training sample, like after doing the train test split, is reserved as a validation set, which is used to tune hyperparameters for our model. So one question that is pretty common is like, why do we want a separate data set for validation and testing? So anyone has any idea about this? Feel free to answer in chat or unmute.
Is it because if we use validation data from test data, it would be like kind of cheating?
Yes, that is correct. Okay, so basically if we evaluate, so if you use our test data set to tune hyperparameters for our model, and then evaluate on the same test data set. So yeah, that would basically mean we have trained our model on the test data set because we used it to pick the set of hyperparameters that works best for our network. So naturally, the model is going to do better on the same test data set because yeah, it's being used to tune the hyperparameters. Okay, someone said we don't want the hyperparameters to be solely for test data. Okay, I'm not sure what this means, but yeah, I guess
I was just answering the question, but I was kind of late.
Yeah, I guess you're on the right track. Okay, yeah. Okay, let's walk through like how many batch gradient descent like work over the course of an epoch, which is like when the network has gone through an entire iteration over the whole data set. So first we divide our data set into batches, and the batch size is m. So that's a hyperparameter that we have to choose. And so for each batch, we have to feed the inputs of each sample into our network, and then we calculate the partial derivative of our loss function with respect to each weights and biases for each data or each sample. And then lastly, we have to take the average of all the partials over the entire batch, and then we update our weights and biases accordingly. I guess depending on our learning rate. So that's pretty much it. Okay, we've prepared some discussion questions. So these are kind of open-ended, so I'll give you guys a few minutes to think about it. Feel free to put your answers in chat or unmute. All right, someone said number of hidden layers, more hidden layers will slow the program down. Okay, yeah, that's correct. I guess to be more specific, like having more hidden layers will increase the time it takes to train our network just because there are more weights and biases. But yeah, I think the idea is right. Learning rate can speed program training with higher rates. Yes, so learning rate is another example. However, there are some pitfalls with having like a learning rate that's too high. So for example, like the loss might overshoot the minimum that we want to converge to, and then it might even make the loss diverge to infinity, which is bad. Yes, exactly. Okay, I'm gonna launch this poll just to make sure everyone is, I guess, agreeing. Okay, I'm gonna give it 10 more seconds. Okay, so most of you picked the number of neurons and the number of layers. So yeah, that's correct. I think 2 people picked weights and biases. So those are actually not hyperparameters. Those are just regular parameters because yeah, weights and biases are being learned by the network during training. So that is not what hyperparameters are. Okay. Okay, so another question, but this one is, I guess, more concrete. This one's actually on the MNIST data set. So yeah, suppose we're doing mini batch gradient descent on our network, and then our batch size is 10, our training set has 60,000 images, and our test set has 10,000 images, and we want to train it over 40 epochs. So that means we're gonna go through our entire data set 40 times. Okay, so the first question is just how many images are used in each gradient approximation. So feel free to answer that in chat. 10 is the correct answer because that's the batch size. So for every batch, we're gonna approximate the gradient and then make an update to the weights and biases. Very good. So the second question is, how many times is the network going to update its weights and biases? So this one is definitely more tricky than the first one. I'm gonna give you guys a minute. Okay. Someone said 40. So does you guys, okay, someone else said 240,000. Okay, so multiple people said 240,000. That's interesting. So do you guys want to explain your reasoning behind why you picked your answer? $24,000. Okay, we're getting a lot of different answers. Okay, someone said 60,000 training data divided by 10, so that's 6,000 times 40. So yes, that is the correct answer. Yeah, so 240,000 is the correct answer. But yeah, so basically, yeah, you divide the entire training data set by 10 because that's how many times we're updating our network for every epoch, and then we have 40 epochs, so we multiply that by 40. Okay, good. So the next question is, how many times then will the network feed forward? So remember, feed forward means making a prediction. Okay. So I guess, yeah, so one epoch is basically means the model goes through the entire data set once, but for each batch, like we're doing a feed forward and backprop. Yeah, so for each batch, we're updating our gradients. For each training sample, we're doing the feed forward and backpropagation. But so we're doing that for every sample in our batch, and then we compute the average gradient over the entire batch to make an update to the weights and biases in the network. Okay, so the network will basically feed forward for every sample. And also there's the test data set, so don't forget about that. Because feed forward is basically making a prediction. So an epoch is doing the entire thing over again. And a batch is what training sets divide into for each. Yes, that is correct. Precisely. Yeah, so once we go through like all the mini batches, then we've essentially completed an epoch because we go through the entire data set once. Yeah, remember there's the test data set. Seven. Okay, we're getting different answers. So someone said 70,000 times 40. So do you want to explain your reasoning?
I added the training set and then the test set, so I got 70,000. And then I divided by 10 because you fast forward or you feed forward once per batch. And then you do that for 40 epochs.
Okay, so I might be a little bit inaccurate about like not precise about this, but for every sample, we're doing the feed forward. So I just want to clear that up. And then we make an update for every batch. Make an update to our gradients.
Okay, so to make sure, each sample, meaning like if you were to run one batch, you'd feed forward 10 times.
Yes, because we have to compute we have to make the prediction for every sample. And then I guess for that matter, we're also going to backpropagate 10 times to compute the gradient for each sample. And then we're taking the average of those gradients. And then we'll basically just consider that to be the gradient for the batch. And then we're going to make an update to our weights and biases, the average gradient. Hope that clears things up a little bit. Okay, so the correct answer is actually 60,000 times 40 plus 10,000 for testing, because we don't actually run our model through the test data set like for every epoch. So we usually do that at the end. But I guess some of you might be confused with the test data set with the validation set, because for validation, we do run it like after every epoch, I believe. But yeah, for the test data set, we only want to run it once after. Yeah, we only want to evaluate our model once after the training is done. So yeah, hope that clears things up a little bit. Okay, I guess the last question is, how many times will the network backpropagate? So this is pretty similar to the previous question with like a slight twist. So we're actually running short on time, so I'll give you guys like a minute.
So real quick, I know I'm jumping backwards, but going to part B, when do you update your weights and bias? Is it after you finish running through one sample, or after you finish training the batch?
Yeah, so so we update our weights once after each batch. But you have to feed forward and backpropagate 10 times in order to figure out what the average gradient for the batch is.
Got it. Okay, that makes sense. Thank you.
Yeah, no problem. Okay, someone said 60,000 times 40 because no backprop on testing. Yes, that is the correct answer. Very nice. All right, so it looks like most of you are getting it, so that's very good. Okay, we have one more discussion questions. I guess I'll just launch a poll because we're running short on time. Wait, okay, we do have a poll for this one. Okay, so this is more about like, I guess, overfitting. Which model would be better? Okay, I guess better in this case means like a better performance on the test data sets. Yeah, that better is kind of a little vague. So yeah, better refers to test accuracy. Okay, I'm gonna give it 10 more seconds. Okay, so most of you picked model 1, so that's correct. Model 1 would have a better test accuracy because it only trains over 200 epochs. So that's usually like around the ballpark of like how many epochs you want to train a neural network over. And Model 2 trains over 1,000 epochs, so that's way too much, especially for the MNIST data set. So yeah, hopefully that makes sense. Okay, so we actually have, okay, sorry, go ahead.
Sorry. Oh, I was asking if you could please, like, I guess when you guys have time, go over the process of like feed forward and back propagation one more time.
Yeah, sure. We're actually running a little low on time because, yeah, we have 10 minutes left.
You can definitely come in for.
We can
office
definitely
hours.
go over office hours, or we also have like some resources that we linked, especially the playlist for 3 blue 1 brown on neural networks. That is always super useful because, like, I think the animations for those videos are really useful. But yeah. Okay, so one last thing, like, please install Anaconda if you haven't done so already, because we'll be using it for the 6th workshop. So it should only take you about 20 minutes. And if you need help, you can always like come to office hours or read this document that we prepared. So yeah. Okay. Okay, yeah, here are some resources. There's an article on activation function. There's actually a YouTube video on neural networks. I believe that's the one made by 3 blue 1 brown. And then yeah, I guess more YouTube videos. Okay, thank you all for coming. I know that was a pretty math intensive workshop with a lot of concepts. But yeah, thank you all for sticking through. Please remember to fill out our feedback form because that is always like really useful for us. And
also,
yeah,
we really appreciate the participation today. It was really, really good. I hope you all were really participative.
yeah, that was
Good stuff.
That was really helpful.
Yeah, good stuff, guys. Good stuff.
Okay, I'm gonna stop the recording.